Yes. Yeah, the end of this title is supposed to be where all the eyes are. Originally they were blinking because they can't quite see in the dark. So it's what goes on in the dark of galaxy halos is the official title. And I know this is a little late for Halloween, but it's still scary in the dark, so it fits in. And I'm coming from the University of Michigan. I moved there about a year ago. All right, we might have a little bit of a problem here with some of the transitioning, so we'll see if we can get this going. I'm not sure this is going to work yet. I got the eyes going. There we go. Okay, we'll try this. I might have to stand over here for a change instead of walking around like I normally do. But when we look at the dark of galaxy halos, we're actually going to be looking at the dark from the gaseous perspective. So we know that galaxy halos have these extended, huge dark matter halos around them. What I'm going to be focusing on is the gas within that huge extended halo. And I'll be talking about two types of structures within galaxy halos. In particular, what I'll focus on are what's labeled here as HVCs, or high velocity clouds. And these are dense concentrations of cool neutral hydrogen that kind of surround our galaxy. They come in a wide range of sizes. Some of them are very small, some are very large. They have a wide range of velocities as well, extending all the way out to positive 450 to negative 450. And then the idea is that these gaseous clumps are our star formation fuel. That's how the disk of our galaxy has continued to form stars over time, is by accreting these high velocity clouds of cool gas. And then beyond that, looking within the gaseous halo, in between all these high velocity clouds, there could be a very diffuse gaseous halo extending out, surrounding those high velocity clouds. And those two together could actually harbor a large percentage of baryons as well. There's the issue of the missing baryons in galaxies. You only can account for about 8% when you add up all the stars and the gas, ISM, in the disk of the galaxy. And so there's some new models out there that actually say a lot of those missing baryons are locked up in these gaseous halos. So I'll be using these specific clouds to constrain those models a little bit. All right, these are who the eyes were. These are people who I've worked with specifically on some of the two things I'll be talking about today. In terms of GALPHA, that stands for the Galactic Arecibo L-Band Feed Array Survey. I'll be getting to that later in the talk, and these are some of the main players working with me on that survey of the high velocity clouds, galaxies, and local group. And then when I get into talking about other galaxies and probing the gaseous halos of other galaxies, these are some of my main collaborators on that particular project. Right. So how do we go about, just to set the scene a little bit, how do we go about forming one of these beautiful spiral galaxies that Hubble is so good at taking pictures of? I just grabbed some of these from the Hubble Heritage site to show you an example. Well, I guess the standard model, right, is that large-scale structure, you form structure in the universe, and where the filaments cross, etc., you start to form a galaxy in many cases. So the dark matter clumps and coalesces into a more massive dark matter halo. The baryons generally follow that dark matter and fall in and eventually form what could be the spiral galaxies you just saw. If you go into the more details of the model, the gaseous inflow is how you get that baryonic component then in that resulting disk. So how do you get those baryons down into that disk? The traditional model is that you have this gaseous inflow going on. And so what goes on, and this is just going to be a simulation by Moore et al. Showing you what the dark matter does in terms of clumping. I'm sure you've all seen this type of movie before. But what goes on with the baryons is the dark matter halos start collapsing. Then the gas shock heats to the halo temperature, and eventually that gas cools and falls in. That's the traditional model, back to White and Reese in 1978, and subsequent models after that. This is the traditional model that's been used. Dark matter halos collapse, the baryons follow it, shock heats, cools, falls in. That falling in fuel forms the baryonic mass in the center of the galaxy. So let's go, okay, so that's the traditional model we have for how a galaxy forms and how that baryonic material gets in there. Let's look at evidence that gaseous inflow actually occurs. Okay, we see lots of gas there, but what's to argue that we don't have a closed box model that all the gas continues to recycle, but that we do have some gaseous inflow occurring over time? The evidence is basically, one, we have continuous star formation in galaxy disks. For a galaxy like the Milky Way, we get about 1 solar mass per year. There are gaseous halos in existence. That's kind of evidence it probably has to inflow at some time. And then the strongest evidence is actually this metallicity distribution of the stars, really, I would say. And that's traditionally known as the G-dwarf problem. I have a slide here that'll explain that a little bit more. This is actually K-dwarfs here. So what we have here is the metallicity distribution of a large sample of K-dwarfs. This is Chris Flynn and collaborators' work, where solar metallicity then is about 0 here. And what the dots here represent the actual data. The solid line represents a fit to that data. So how did they get this fit to the actual data for these K-dwarfs? Remember, K-dwarfs are stars that are very low mass. So they've been around a long time and are tracing the metallicity distribution of our galaxy over a long period of time. And so the solid line is a model which has that infalling fresh gas. So fresh in the sense of relatively low metallicity gas. And when you try to have models without any type of infall, you just can't reproduce that type of distribution for the metallicity of the stars. So that's arguing that you do have to have some type of fresh star formation field continually raining down onto the galaxy disk. What's some more evidence for some type of gaseous inflow, in particular from that inflow coming from the extended halo and not just from individual satellites clumping together and that all coming into equilibrium? This is kind of indirect evidence that you could have inflow directly from the intergalactic medium and not just the dwarf galaxies coming together and bringing in their baryonic matter. This is interesting results by Venn et al. And what this shows you is, again, the metallicity distribution of stars in both the thin disk of our galaxy. The thicker disk is the green, so you can just say disk stars are the green and the red. And then halo stars are the blue stars in this picture. And then the open boxes here are actually the dwarf satellites of the Milky Way. And we can see here the metallicity range of these dwarf satellites is rather different than the metallicity range of the stars in the Milky Way. And so this is evidence that they've kind of built up in different ways, probably, right? So there might have been some of those dwarf satellites that were integrated into the Milky Way disk, but then the Milky Way probably also had some other type of fuel raining down onto it to get that different distribution of metallicity. So this is, again, some type of evidence that continuous accretion must occur in some mode. It's definitely a more indirect constraint. So what's the problem then? Well, we have this problem in Michigan quite a bit. But the problem I'm talking about in terms of the gaseous inflow models. So you see evidence it occurs, and we have the models that predict it occurs. What's the problem? And this is something many of you are familiar with, especially if you work on clusters, is the overcooling problem. Those traditional models, all the gas falls into the center very, very quickly, and it overproduces the mass in the center of that dark matter halo. So all the gas in the halo cools at very early times in the White and Reese models, etc. And so then you end up with the mass of the galaxies overestimated, and there isn't any gas left in the halo in those models either. So you do need some type of solution for this overcooling problem. What's traditionally been invoked quite often for clusters, for instance, and many of you can tell me more about this, is feedback. For spiral galaxies, having excessive feedback is a little more difficult to invoke. So what's been done recently, there's been 2 models put together, and these are progressing quite rapidly, is a way to solve this overcooling problem. And the way this has been solved is by having the halo gas fragment as it cools and form individual clouds as it rains in. So what we have in these models, and what I'll be focusing on, the model of Naller and Bullock in 2004, and then Fukugita and Peebles 2005 have also put out an AstroPH article discussing a very similar model. There's also been an early model trying to simulate something similar, but they're not quite have the physics up to the models that have been developed by these 2 yet, where you're actually able to simulate this in detail. But what you have in these models is you have some type of pressure-supported hot gas out in the halo, extending out to about 150 kiloparsec. And as the gas is starting to cool, it's thermally unstable and it begins to fragment into individual clouds as it cools. And those clouds then stay in the halo. Initially, they're moving uniformly throughout the halo, and then eventually, as they collide with each other and undergo some ram pressure effects, they begin to fall down to the disk and feed the disk of our galaxy. So what these models typically predict is on the order of 2 by 10 to the 10 solar masses of condensed clouds. That would be the individual cooler clouds. And then 4 by 10 to the 10 solar masses of diffuse hot halo gas, all within about 150 kiloparsecs at a redshift of 0. So this is a prediction we can test. The clouds then would have typical masses of about 5 by 10 to the 6 range. and this is set by conduction, Kelvin-Helmholtz instabilities, etc. This may range everywhere from 10 to the 5 up to 10 to the 7, but that's the general range. All right, and as I mentioned in the intro, this is very, very appealing to the missing baryon problem, because as you can see, this is a lot of baryons to be hiding out in a typical L-star galaxy. So if this is actually a phenomena that's out there, this could be important to that problem. All right, so this, if you like pictures better than words, I made this little picture showing you what the model would generally be like, where you have this diffuse hot halo. It wouldn't have this really sharp boundary where it just kind of fade out as you go out. And then you're forming these little clouds as that hot halo begins to cool and fragment, and eventually those clouds begin to infall onto the galactic disk.